Namaste and welcome to this lecture on linear algebra through geometry. And in the last class you would have studied about how to solve system of equations using elementary row transformations. Some of these elementary row operations, like 3 of those elementary row operations we have seen in the last class. I am quite sure the examples that we worked out, Professor Krishna Kumar worked out, would have given enough insight to how to solve a system of equations using elementary row operations, and that is exactly what we called as our Gauss elimination and techniques. Now, what we have here is we are going to ask a few questions. The questions are, in this lecture what we are going to look at is we are going to see like how is this elementary row operation actually effected, right? How is it done? How do we, let us say, swap 2 rows of a matrix? How do we, let us say, add a scalar multiple of a row with another row of the same matrix? How do we scale a particular row alone in a matrix, because those were the 3 elementary row operations that you studied in the last class. So how are we going to do that? Is it like like what we write, is it going to be that way, or is it going to be a different way of doing it? And we have another very interesting and important question to answer. What is that? How do these elementary row operations that we do, how do these guys actually preserve the solutions? How do we know that the solutions are going to be the same? Right, the solutions have to be the same. You do a lot of operations on the rows and the system actually keeps changing. Your system of equations, what you had as Ax is equal to b, in the beginning when you started doing these elementary row operations, the system actually changes to say some A star x is equal to say some b star. How do we assure, I mean that is because of your row operations that you do. So what is the guarantee that the solution is going to remain the same? Will the solution remain the same? Of course we have seen the examples which says, look, finally when you converted everything to an upper triangular matrix and you solve for the system of equations, you ended up getting the variables, I mean the unknown values or the values for the unknowns, and you plugged those unknown values into the original system of equations and you found that the left hand side was equal to the right hand side. I mean that sounds magical. Like how does it even happen? Like what goes behind this? What is it that is happening? What is the intuition, or what is it that is happening behind such that the solutions remain the same even after doing all these kind of operations? So we are going to answer those questions in this lecture, right? So the focus of this lecture will be answering certain questions in an intuitive manner, try to understand like what is happening behind these elementary row operations, how are we carrying out these elementary row operations, and so on, right? That is what we are going to look at in this lecture. Okay, so let us go. Recall that we had the following elementary row operations. Recall the elementary row operations that we had. So what are the operations that we have? The first one probably it was row swap. Let us say the row Ri got swapped with the row Rj of the same matrix, and the second one probably we replaced the row Ri with k times Rj, where k times Ri, we replaced a row with a multiple, kth multiple of the same row, where k is a real scalar. And the third operation that we did was pretty interesting, because we said Ri, you are going to replace the ith row with ith row plus k times another row, k multiple of another row. Now at least if you look at the first one and the second one, the equations are going to remain the same. There is no change in the set of equations, because if you swap 2 rows the equations order change, So you expect the system of equations, linear equations, to have the same solution, which really, I mean, there's what do you call, there's no surprise about it, right? What was the first equation is going to become the second equation, what was the second equation is going to become the first equation. Therefore the we've seen the geometry, we see that okay, both are the same lines, and the lines, if they are intersecting, they are going to intersect at the same point. Only thing is the order in which the equations appear has changed. And the second case, you are going to replace one row with the multiple of the same row, which means throughout you are going to multiply with the same scalar, both left hand side and right hand side, effectively saying that look, I have the same set of equations, therefore the system of equations, I mean the solution does not change. How about this third one? Like, how are we guaranteed that when we do this third operation, the solution to the system of equations remain the same in spite of doing all these kind of operations? That is something which you are going to look at. And before we get into these things, we will see how are we going to do these elementary row operations on a matrix. Suppose I say, look, if I have a 3 by 3 matrix and then I tell you, look, swap the third row with the second row, how are we going to do it? It is not just like picking the row elements and then dumping it in the second row, and picking the second row element and dumping it in the third row. It is not that. There must be a way to do that. So how do we do it? And that is exactly what we are going to look at now. And what we will do is we will go on to look at the insight behind these row operations not changing the solution space also. That is also something which we will focus now in this lecture, right. So let us go ahead. So the first question, or the first thing that we are going to do is we are going to look at how do we carry out, these row operations. Right. So that is the question that we have. How do we carry out these row operations? How do we do it? Let us look at this. Say for example, I want to do a row swap. This corresponds to the row swap operation, right. Row swap operation. Now let us see how do we do that. We will again revisit this when we do vectors, but we will do it from a different context, where a row swap is going to look, it is going to be interpreted as something else. We will wait what that interpretation is till we get to the idea of vectors in 2 dimension, but let us just understand like how do we do this row swap operation. Okay, so let us take this matrix. Let us say A is equal to, let us say A11, A12, A13, A21, or let us do a 2 by 2. Why do we even go to 3 by 3? Let us then go to 3 by 3. A11, A12, A21, A22, and we have our x unknowns to be this matrix x1, x2, and on the right hand side we are going to have this matrix B is equal to B1, B2, basically capturing our system of equations Ax is equal to B. Now you have already seen that if you want to solve for Ax equal to B, what you do is you end up augmenting this matrix A with that column B, and then try to do the row operations on the augmented matrix. You do not do it on A alone, you are going to augment that matrix A with the vector B, and then you are going to the column B, and then you are going to do the row operations on the augmented matrix. So we are going to say row operations on the augmented matrix. Right. So let us see how it is done. So I have this matrix A11, A12, A21, A22, and I have my augmented matrix, the column augmented, which is B1, B2. Now from here, where do I want to go? I want to go, let us say I want to swap R2 with R1. That means R1 now becomes R2 and R2 becomes R1. So I want to look at that. So how do I do it? So what is the result you have? the result is basically A21 A22 augmented with B2 and A11 A2 A12 this is B1. So, this is going to result in this. So, the question is how do we do it? Okay, let us do this. Let us see if we can look at this and try to understand it easily. So, suppose I take this matrix identity matrix 2 by 2 and then multiply this A augmented with B, what do I get? I basically get A augmented with B. This is the matrix that I get. Now, it's the operations are called as elementary operations, which means what I am trying to do is now I am going to try to modify my identity matrix with certain values and then I am going to do it like a matrix multiplication, and that is exactly where I mean we are again going to do this matrix multiplication to carry out row operations, right. So, what are we going to do? So, what I will do is I will change this. So, I have my identity matrix, but I want to change. So, let us look at this simple stuff. Let us just take this case where I have A11 A12 A21 I just have this, and here I want to get to A21 A11. So, how do I do this? We will see it at a later point of time that you can take this matrix to be, let us say, PQRS into A11 A21 gives me A21 A11, which means we will see this the value of P, if you say P A11 plus Q A21 is equal to A21, A11 is does not even exist in the first row here. So, naturally that fellow has to become 0 and A21 comes up, so make that fellow as 1, and R you see this A11 has to come to the second row. So, this is what is going to be there, and A21 does not exist in the second row. So, that becomes 0. So, if I take this 0 1 0 0 into A11 A21, I will end up getting A21 A11. Now, that is exactly the matrix that we want to multiply or to pre-multiply this augmented matrix to get to the row swapped version of the matrix A. So, what are we going to do? So, we are going to say that if you want to do row swap operation, what you do, you try to use this matrix, which is basically 0 1 1 0. You multiply pre-multiply this augmented matrix, which is A11 A21 A12 A22 B1 B2. Now, that is going to give you A21 A22 B2 A11 A12 B1. So, all the row operations are going to be effected in terms of the matrix multiplication. In fact, if you look at a 3 by 3 matrix or any other n by n matrix, if you want to swap any two rows or you want to jumble up the rows, you end up getting what is known as a permutation matrix, which will help you reorder your rows, permute your rows, right. So, that is what we are going to do. Now, how are we going to effect the second one, the second row operation, where we are going to look at replacing a row with the scalar multiple of the same row. So, which means we have this, I have say A B C D again, and I am going to multiply this with, let us say, A11 A12, or let me do this, okay, A11 A12 A21 A22, and this is going to give me, let us say, A11 A12 k times A21 and k times A22 excuse me, this is what I want. How do I do that? Now, if you look at this, suppose again we will go to the form of identity matrix. What are we going to get? If you multiply this, you are going to get A1 1 plus B A21 is equal to A11, and A times A12 plus B times A22 is equal to A12. So, what are we going to get? So, this matrix is going to be, so let us write that expression first of all, and it will be easy to understand. So, what do we have? We have this A times A11 plus B times A21 is equal to A11. Similarly, A times A12 plus B times A22 is equal to A12. Now, this clearly says what is the value that we are going to get. Okay, let us do this from here. Let us get the value of A and B. Similarly, let us look at the second equation, the second one. So, we have C times A11 plus D times A21 is equal to K times A21, and what is it that we have? We have C times A12 plus D times A22 is equal to K times A22. Now, if you look at this equation, this A21 term does not appear at all on the right hand side. So, A is equal to 1 and B is equal to 0. Here again, if you see, A is equal to 1 and B is equal to 0. So, the matrix is basically 1 0. If you look at this pair of equation, what do we see? A11 does not appear, so C is going to be 0. A12 does not appear, so C is going to be 0, and D, it is A21 and A22, and D takes a value K. So, this is going to be the matrix which is going to scale. If you want to do this, you end up pre-multiplying our matrix, coefficient matrix, let us say A11, A12, A21, A22 to get A11, A12, K times A21, K times A22. So, that is the matrix which is going to help you get the scale a particular row in a given matrix. The third thing that we have is most interesting. The third thing that we have is our this matrix, this operation, which is Ri is equal to Ri plus K times Rj. This is what we have. Now, how are we going to do this? If you quickly do the same technique that I did previously, you will see that this is the matrix which will help you gain this. So, again let us probably quickly do it: A, B, C, D, and let us take this to be A11, A12, A21, A22. So, what is this going to give me? Ri is equal to Ri plus Rj. Let me say for here, let me say R2 is equal to R2 plus K times R1. Right. So, what am I going to get? R2 is equal to R2 plus K times R1. So, R1 is going to remain the same. I am going to take A11, A12, I am going to take A11, A12, and in the second case this is going to be A21 plus K times A11, and this is A22 plus K times A12. This is what I have. So, again if you do all this stuff, what we get? We get A into A11 plus B into A21 plus K11 is equal to A11. That is what we have. So, if you try to do this element wise comparison, we will end up getting this. It is 1 0 K 1. That is the matrix which you should be doing pre-multiplying, which you should use for pre-multiplying the given matrix A11, A12, A21, A22 to get A11, A12, and you have A21 plus K times A11, A22 plus K times A22. Now, you can change the position of K here. If you in that case R1 will become, if you swap these two guys, you end up getting R1 is equal to R2 plus K times R1, and R2 will remain the same. So, you can do that. You can, again it can be done in all kind of high dimension matrices and so on. So, the question now is, having done all these things, every elementary row operation. So, the moral of the story is every elementary row operation that we do, elementary row operation or every row operation that we do is basically carried out, is basically done through matrix multiplication. So, is done using matrix multiplication right, In fact, how is it done? You basically do pre-multiply the given matrix with the necessary row operation matrix, so elementary matrix. So pre-multiplication we do in fact, right? Right. Okay, so this is basically how we carry out the elementary row operation. Now the question, second question that we have to answer is basically how are the solutions going to remain the same? So the first thing that we have is the following. So let us say we did row swap. Let us say we had a simple example like, okay, a11 x1 plus a12 x2 is equal to b1 and a21 x1 plus a22 x2 is equal to b2. This is a12 is equal to b2. This is what we have, and we have our matrix form, which is a11 a12 a21 a22, and we have x1 x2 which is equal to, let us say, b1 b2. Now what are we trying to do here? We will augment the matrix. So we have augmented matrix which is going to look like this. There is going to be a11 a12 augment with b1, a21 a22 augment with b2. So this is what we have. And if you look at this, this corresponds to say some line L1, this corresponds to say some line L2 in 2D. Now if we do a row swap, so we have row swap. So if we do a row swap, what do we get? We basically end up getting this augmented matrix which is a21 a22 b1 and sorry b2 a11 a12, and that gives me b1. Now if you again look at the system of equation, it is just that the second equation, the order of the equations have changed and the lines have not changed. The lines are going to be the same, but when you look at it in terms of vectors, something else happens. As I said, like we will wait for that suspense probably when we do this vector, but right now what we see is the lines are the same. Whether you take the first line, I mean you draw the first line and then do the second line, or draw the second line first and then do the first line, you are going to have the same point of intersection, which means it is very clear that the solution is not going to change. And in the second case, when where we multiply it by a scalar, we are going to multiply the scalar throughout a particular row in the augmented matrix, and in which case still the line is not going to change, because it is a common factor that you are going to multiply in the left hand side and the right hand side. You are going to multiply it on either sides, therefore nothing changes there. Now the problem comes when you look at the system of equations and you do this elementary operation. I mean these are I would not say obvious, these are pretty clearly seen that if you change the order of the equations still remain the same, nothing changes, therefore solution remains the same. Scaling a particular row or scaling a particular equation by a constant does not change, because throughout you have multiplied, essentially it is equivalent to saying, okay, I retain the same equation. So the solution, you can very clearly understand that there is no way the solution is going to change. But what about the third one? That is exactly where we are looking at. So we want to look at Ri plus k times Rj. So when we do this, the question is how is it that the solution remains the same? That is something which we want to look at. So we will, what we will do is we will take our simple example, whatever we did, 2x1 plus x2 is equal to 3. We will look at this and we will take x1 plus 2x2 is equal to 3. We will take this system of equations. Now when we do this, let us take the augmented matrix which is say 2 1 1 2 and we have 3 3. This is what we have, and let me do R2 tends to R2 plus k times R1. Right, I am going to do something here. K times R1 is going to be like this. So I have first row is going to remain the same, 2 1 3. The second row is going to be 1 plus 2k, 2 plus k and 3 plus 3k. This is what I have. Right. Now what we do is we plot these lines. Let us see when we, so what are we going to do is we will plot. The first line is not going to change, it is going to be 2x1 plus x2 is equal to 3. Okay, let me write it here. So 2x1 plus x2 is equal to 3, and the second line is going to be 1 plus 2k times x1 plus 2 plus k times x2 is equal to 3 into 1 plus k. This is what we have. Looks like the coefficients are all different. It is 1 plus 2k somewhere, it is 2 plus k somewhere, and it is 1 plus k somewhere. It is not scaling by the same thing, there is something else that has happened, but out of nowhere we see that the solutions remain the same. So, what actually happens behind, that is exactly what we want to look at. Now, what we will do is we will try to plot the second equation. Let us retain the first equation as such. For the second equation, what we will do is we will take different values of k. Let us take k is equal to 0, let us take k is equal to 1, k is equal to minus 1, k is equal to 2. Let us do all these things and then try to plot the second line in each case. So, let us call, if this were to be called as L2, now what I will do is let me call this as L2k. The superscript k indicates what is the value of k that I am going to put. I am not going to do exponentiation and all, it is just going to tell me what is the value of k that I have used. So, let me do this. So, what I will do is I will look at L2, when I use k is equal to 0, this is going to look like the second equation is going to be x1 plus 2 x2 is equal to 3, which is the same as what we had before. Therefore, the things do not change, the solution is going to be the same. Now, let us look at L2 of 1. What am I going to get? I am going to get, if I put k is equal to 1, I am going to get 1 plus 2 into x1, 1 plus 2 into x1 is 3x1, 2 plus let us say 1 into x2, that is going to be 3x2, and here we are going to get 3 into 1 plus k, that is going to be 3 into 1 plus 1, which is say 6. Let us look at L2 of minus 1. What happens? That means when you put k is equal to minus 1, let us see what happens. So, if you put k is equal to minus 1, it is 1 minus 2, which is minus 1 x1. So, I am going to have minus x1 plus 2 plus minus 1, that is going to be giving me x2, then 1 plus minus 1, that is going to be 0. So, this is going to be the next line. Let us look at L2 of 2. L2 of 2 is going to be even different. So, it is going to be 1 plus 2 into 2, that is going to be 5x1 plus 4x2 is equal to 3 into 1 plus 3, 1 plus 2, which is 3 into 3, which is 9. So, these are all the lines that we get. Now, let us plot all these lines and then see what happens. So, let us plot these lines. So, we are going to get the, let us retain the first line, which is basically x1 plus 2x2 or 2x1 plus x2 is equal to 0. So, 3. So, let this be L1, which corresponds to 2x1 plus x2 is equal to 3, and this is the line. Now, when you have the second expression, which is basically second equation, which is L2 of 0, let us see how L2 of 0 looks like. L2 of 0 is basically x1 plus 2x2 is equal to 3. So, x2 is going to be, when it is 3, I mean when x2 is 0, x1 is 3, when x1 is 0, x2 is 1.5. So, it is going to be here. So, let us assume that okay, it is going to cut like this, and that is the point 1 comma 1 where the two lines meet. Now, let us take the third expression, the third equation that we have, which is L2 of 1. What was L2 of 1? Let us look at that. L2 of 1 is 3x1 plus 3x2 is equal to 6. 3x1 plus 3x2 is equal to 6. Now, how is it done? When you put x1 is equal to 0, you get x2 is equal to 2. So, this was 1.5, let me make this to be somewhere 2, and when you have x2 is equal to 0, x1 is equal to again 2. So, you get, so this is going to be 2. So, we will see that this line goes like this, and what is interesting is this line, which is basically L2 of 1, intersects L1 at the same point as L2 of 0, 1 comma 1. Let us look at the next one. The next one is basically L2 of minus 1, which said minus x1 plus x2 is equal to 0, minus x1 plus x2 is equal to 0, x1 is equal to x2. That line goes like this. This is my L2 of minus 1. That also intersects the first line at 1 comma 1. Similarly, if you take the next line, that will also intersect at 1 comma 1. So, what is basically happening? This is like how we operate on the door. If you look at the door at the end of in your room, what is that? The door is basically hinged to the wall at a particular point, and that point does not mean that entire thing does not change if you keep rotating the door, and that is exactly what happens here. these lines that we have, when you do this R2, I mean Ri is equal to Ri plus k times Rj, where k is some real scalar, for different values of k, you end up getting the lines, different lines, and all these different lines, they intersect with the first line hinged at the same particular point. It is like taking a nail and hammering it at this point 1 comma 1, and then rotating that second line whatever we had, which was L2 of 0, that changing the values of k, you are going to rotate that line, and what we see is the solution does not change. That is exactly the reason, the reason behind this is all these lines, they are they intersect at that particular point, in this case where 1 comma 1, they get hinged, they get hammered at that particular point, they get nailed at that point. And that is exactly, basically what happens is when you change this Ri is equal to Ri plus k times Rj for different values of k, is going to rotate the second line hinged at the solution, therefore the solution does not change. And what we will do is we will see all these things visually, and it creates more excitement. So on that note, what we will do is we will conclude this lecture. We understood like what are the elementary row operations doing, and what is the kind of insight that you have, or what is it that is happening behind these operations, and how are we going to affect these operations. All those things we have seen. In the next class we will look at something more interesting, where we get into the idea of determinants and ranks, rank of a matrix, and Professor Krishna Kumar will be dealing with that. Then I will again come back with some kind of insights, and then we will look at the idea of Cramer's rule, right. So that will be the flow of the lecture for the next couple of days. Namaste. Thank you.